Let's start with this question. This is a Newton's second law question again, right? So all of our problems from this unit, they're all Newton's second law. And remember, really, the main equation for Newton's second law is that the net force, or the one force that can replace all of the forces acting on an object, that's mass times acceleration. And if I want to find the net force, I would take all of the applied forces, all the forces trying to make it accelerate, and I would subtract it from all the opposing forces. Okay, so in this problem, I have a skydiver. So here's my skydiver, and I don't know, maybe they let their parachute out already. Okay, so the skydiver has a mass of 72 kilograms. So I know her mass. Mass is 72. And I know her acceleration. Her acceleration is 4.7 meters per second squared. All right. Now, she's falling. The reason that it's not 9.8 is because she's not falling in a vacuum, right? There's not just one force acting on her. There's two forces acting on her. So if I were to take her, right, I'm going to take her and move her over here. If I were to take her and kind of draw out the forces, there's one force that's pulling her down, and that's her weight. Remember, her weight is mass times gravity. And then there's one force that's pushing her up. And that force in this problem is air resistance. And it's actually asking us, what is the force of the air resistance? So this is my question mark right there. Okay, so for this problem, I'm going to have to use the F net equation first. So I have F net equals mass times acceleration. And the mass is 72. The acceleration is 4.7. So the one force that could replace these two forces is going to be 72 times 4.2. Can someone type that in the chat box or shout it out? It's going to be like 300, 302. I'm sorry, what was it? 302.4 newtons. Okay. And then, okay, I'm going to have to use the equation that says F net is all the applied forces minus all the opposing. So we have two forces. The weight is going to be an applied force. And the reason the weight is an applied force is because you guys know if you jump out of an airplane, you will keep falling, right? So you are accelerating towards the ground. So I'm just going to make gravity 10. I'm going to round it to 10. And that way her weight would be 720 newtons. So the air resistance, that's a question mark. I still don't know what that is. But I know that her weight is 720. So now I could plug everything into this equation. I know that the net force, the one force that replaces all the others, oops. My pen just went crazy for a second. The one force that could replace all the others is 302.4. Okay. And that's equal to the applied force, which is 720, minus air resistance. Now, if I want to get this on the other side, it's being added because it has a plus in front of it. Well, it has nothing in front, which means that there's a plus. So I'm going to subtract it from both sides. When I do that, those go away. And it leaves me with a negative force opposing equals 200 and... No, I'm sorry, 417.6, is that right? 417.6, okay, newtons. And that's negative, right? It's negative. So there's a negative on both sides, you guys, they just cancel out. And the opposing force is 417.6 newtons. If you wrote this down, the opposing force is negative 417.6. That would be that would also be acceptable, because a negative force, it's a decelerating force. It's a force that's causing you to slow down. Because remember, the negative just implies direction. The opposing here also implies direction. It also implies that you're slowing down. So if you write force opposing, you don't have to write the negative, but you still can if you want. Yep. Air resistance is just like friction. It always opposes motion. Yep. So does this make sense, this question? Are we good on this one? Any questions on it? Okay, well then I'm going to do another one. I have 3 total that I'd like to do, just to kind of get you back. We've been working on these incline problems for so long. I kind of want to get you back to some of these other problems. So here's another review one. This is actually off one of your homeworks, right? So I figured we would do it. I have a NASCAR driver, and the NASCAR driver enters the pit area, which is 0.55 kilometers long. Okay, so the that's a distance, right? The distance is 0.55 kilometers. Now, do we ever use kilometers, or do we always use meters?
Meters.
Right, meters. So to put this in meters, I would have to times it by 1,000 or move the decimal to the right 5 places. So it would be 550 meters. Okay. Now, did we do this problem before? I feel like we did. No, maybe not. Okay. All right. Maybe I did it with the other class. So if you're this driver, right, and you're going into the pit area, I don't know if you guys know about NASCAR, but that means you're making a pit stop. All right. So your final velocity is going to be 0. The only time you go in there is when you have to get your tires changed, you need more gas, right? They got to do something on your car. So you're making a pit stop. Now your starting speed is going to be 185 miles per hour. And then the mass is 1,885 kilograms, okay? Calculate the minimum force necessary. Now, we also don't use miles per hour. We always use meters per second. So I'm going to convert that before I do anything else. And I'm going to convert it out using 2 separate conversion factors, you guys. You don't have to. I want to get rid of miles. Miles is on top there, so I'm going to put it on bottom and replace it with meters. I want to get rid of hours. Hours is on the bottom there. So I'll put it on top, replace it with seconds. I know that for every 1 mile, there's 1,600 meters. It's actually slightly different, but I'm just going to go with that because that's what I remember from track, right? And then I know that in every 1 hour, there are 3,600 seconds. So I multiply across, and then I divide by everything on the bottom. So 185 times 1,600 times 1 divided by 1 divided by 3,600. Can someone tell me what that is?
$82.2 meters per second.
82.2 meters per second. So instead of using this 185, we'll use 82.2. Okay. Now there might very well be a question on the test where you have to use like your old acceleration equations to figure out acceleration, and then from that do F equals ma. Okay. So the very first thing I have to do is I have to figure out acceleration. I have to use all this stuff. Now you only have one acceleration equation without time. That's Vf squared equals Vo squared plus 2 times acceleration times distance. So this is why, this is why I tell you to keep all the equations in one spot, because we're going to use them all the time. We still get to use them when we come back and we start talking about momentum and It's going to be fun. So we'll put the stuff in here. This will be 0 squared equals 82.2 squared plus 2 times acceleration times 0.55. Oh, I'm sorry. That's wrong. Times 550. Right? Because we only do meters. Okay. So then 0 squared is 0. Can someone tell me what 82.2 squared is?
6756.84.
Okay, so it's 6,756.84. 2 times 550 is 1,100 times A. So then to get, this is being added right now. To get it to the other side, you guys, I would have to subtract it, right? So these two will cancel, and I'll get negative 6,756.84 is equal to 1,100A. And then to get A by itself, I would divide both sides by 1,100. Sorry if I did that kind of fast. That's just our algebra part, right? So then the 1,100 here will cancel. Acceleration equals 6.6-ish. 6 point what?
$6.14.
6.14 meters per second squared. So now I found the acceleration, but I want to find the net force. Okay, in this case, you guys, the net force is also going to be the stopping force. There's only one force acting on the car, and it's an opposing force. When I slam on my brakes, there's no accelerating force. You wouldn't slam on your brakes and slam on the gas, right? Like, that doesn't make sense. So there's only forces trying to slow you down. So F net equals mass, which is 1,885 times my acceleration, which is actually negative 6.14. We dropped the negative on accident here. And the net force is going to equal
negative 11,573.9.
So a negative 11,573.9 newtons. There we go. And it's negative because it's an opposing force. It's a stopping force. It's a decelerating force. So you could have a question like this on the test. You could have a question like this, right? And then here's one last one, okay? And this one has friction. So in this one, I have a girl. She has a mass of 53 kilograms. She's rollerblading down the street at constant velocity. So can someone tell me what her acceleration would be if her velocity is constant?
9.8.
No.
0.
It'll be 0, right? I told you guys, like, you would start to say 9.8 all the time. But if you're not changing speed, it's 0, right? The force that she applies to her brakes is 277 newtons. I want to know what is the coefficient of friction between her skates and the street. So I'm going to draw a little picture here. Here she is, all right? And she's rollerblading. Okay. So she's pushing forward with a force, an applied force of 277 newtons. If the acceleration is 0, the net force has to be 0. Does everybody agree with that? Because 0 times any mass will be 0. So if she's pushing with 277, that means that there has to be 277 newtons of friction going in the opposite direction. So this frictional force has to match her applied force. Because they're the same, net force is 0. Now, anybody who's rollerbladed or biked, right, gotten on a bike, most of the time when you're cruising down the street on your bike, you're actually going at constant speed. There aren't, more often than not, you're just going at constant speed. You're not speeding up or slowing down. What you're doing on the bike to maintain a constant speed is you have to pedal with enough force going forward to counteract friction, slowing you down. So that's what she's doing right here. So now I know her friction force is 277 newtons. Okay. Now there's one other force that's acting here, but it's not acting in the direction of motion. It's the force that's pushing straight down, and we call that the normal force, right? You could call it the perpendicular force, the normal force, whatever you want to call it. And remember, if it's flat like this, the normal force is equal to her weight. And I'm going to pretend that gravity is 10 instead of 9.8. So for this, the normal force would be 530 newtons. Well, now that I know all that stuff, this problem is going to be pretty easy because you have an equation for friction that says the force of friction is mu times the normal force. So the force of friction is 277. Mu I don't know. And the normal force is 530. So to get mu by itself, I just divide by 530. Those will disappear. And then mu would equal 277 divided by 530, just under 0.5, like 0.45. Does anybody have it?
0.52.
Oh, 0.52. Oh, I went the wrong way. Okay, so mu is 0.52. So what that means is that roughly half of the normal force gets translated into friction. So if this were me instead of this girl, mu wouldn't change, right? If I was wearing the same skates, skating on the same street, but the friction force would get bigger because I happen to weigh more than 530 newtons. Just a little more. Okay? So hopefully you guys feel okay with these types of problems. So there'll be these types of problems, and then there'll be our incline problems, all right? But that's all of the problems I could give you on the test. Now, on the multiple choice part, just as a review, there's going to be probably some Newton's first law questions, right? And remember that Newton's first law says objects maintain their state of motion unless acted upon by an outside force. So they keep moving at the same speed in a straight line, unless they're stopped, and then they stay stopped. Okay. Unless there's, and that outside force, you guys, has to be a net force other than 0. And then Newton's second law is just force equals mass times acceleration. So if I have a net force acting on an object that's not 0, it produces an acceleration, and the acceleration is directly proportional to the force and inversely proportional to the mass. So now we get to complete Newton's laws by learning the third law. Does anybody remember what it is or from a previous science class? Even a junior high science class? No? So this is what Newton's third law says. All right? Newton's third law says for every action force, there is an equal and opposite reaction force. So for every action force, there's an equal and opposite reaction force. Now, you probably learned it this way when you were younger. You just may have forgotten. You probably learned that for every action, there's an equal and opposite reaction, right? But it's important that you put that word force in there, right? Because what we really mean is that for every action force that you apply, there's an equal and opposite reaction force acting on the other object in the other direction. So these right here, these two examples, these are really good examples of how Newton's law can come into play with, say, for concussions, right? Because if the action force is a soccer player and their head is bumping the ball, right? There's an equal and opposite reaction force of that ball pushing on his head. For these two football players, this football player is carrying the ball. I think that's Deshaun Watson. Looks like him. And there's a player coming in that looks like Alabama, actually. So this Alabama player is coming in and applying a force head-to-head onto Watson's helmet, right? So that would be the action force. Then the reaction force would be the Watson's helmet pushing back on the other player's head, right? Another way of thinking about this, you guys, is that you can't hit anything harder than it hits you back, okay? Anytime you apply a force to an object, that object will apply an equal force to you in the opposite direction. So I want you to think about this scenario, right? Now, I know that all of you are calm. You all have good coping mechanisms for when you get angry, right? Hopefully. Sometimes when people don't have good coping mechanisms, one of the things they do is they get angry and they punch a wall or something, right? If you punch a wall, there's two outcomes that could happen. Outcome number one, which is the best one for you, is that when you punch the wall, you hit drywall, because most of our houses have drywall, not plaster, right? So you hit the drywall in a spot that's in between the studs, because there are studs that go up that you nail the drywall into. You screw it in, actually, right? And if you punch in between those wood beams that are called studs, you can actually punch through the drywall. And it'll hurt your hand, might cut it up, but you'll be okay, right? Or you could punch a stud, and that's not okay. Usually that's a trip to the hospital. You break your hand, right? If you're trying to punch as hard as you can. And the reason is, you guys, is because if I hit something as hard as I hit it, I get an equal force applied to my hand. In real life, fights that are physical fist fights, they usually don't last that long. And the reason is because if people really are punching each other, and usually, I think it's ingrained in human nature, is that you attack someone's head, right? So you try to punch them in the head. Now, just so you guys know, your skull is the hardest bone in your body for a reason, right? We want to protect that brain. And so if you punch someone as hard as you can in their skull, the most likely outcome is you're going to break your hand, right? So, you can't hit anything harder than it hits you back. And that's why in soccer, your coaches are really, really careful to show you the correct way to head this ball. Because if you don't do it correctly, it can give you a concussion, right? That's a real thing. In football, there are all kinds of rules, and they're getting stricter and stricter about players hitting each other in the head with their helmets. I hear all the time that football players are getting wimpier. That's not true, right? It's just that we're trying to get smarter about protecting their brains. So, anytime there's this helmet to helmet contact, bad things can happen for both players, not just one. Because for every action force, there's an equal and opposite reaction force. And in fact, you guys, most concussions don't actually happen helmet to helmet. You know, when I was a kid and we played football, everyone had to wear knee pads, right? They were just a thing. And now, if you look at any college or pro game, none of the players wear knee pads because they think they slow them down. And so, since nobody wears a knee pad, if this person's knee hits this person's head, it's very likely to result in a concussion for the person whose head is being hit. It can result in a shattered kneecap, but usually not. Usually, it results in just a bad bruise, right? A deep bone bruise, something like that. Yeah. So unless they start regulating that people have to start wearing like knee pads again, shoulder pads are super tiny now. No thigh pads anymore. You know, these kinds of injuries will keep happening. All right. Now, let me ask you this question. This goes back to my wall punching question, actually. I see this all the time, like in college games and high school games. I see it, but not at Leiden. Leiden, I think we still run out of the Eagle, right? If I remember correctly. So when the football players run through these banners, these paper banners usually that rip apart, what experiences the bigger force, the banner or the football player? So I want you guys to type your answer in the chat box. So which experiences the bigger force, banner or football player? I only have one answer. Now I have two. So everybody started out with the same answer, then they kind of switched now, right? Well, didn't I just get done telling you that for every action force, there's an equal and opposite reaction force? And I just got done telling you you can't hit something harder than it hits you back. So the answer here is the force is the same. It's the same on the banner and the football player, all right? But I know, and don't feel bad if you answered this wrong. Okay? Everybody, I shouldn't say everybody, almost everybody thinks that's true. But they have to be the same. Now, the reason the banner breaks is because it can't withstand that much force. So even though the football player might be trying to hit it with all his might, he actually can't exert that much force on the paper banner. So when that banner breaks, there's no more force being applied. If that was a half ounce of force, he was only able to apply a half ounce of force. That would be the action force. And then the reaction force would be a half ounce of force on him. So this is the thing where if you hit the wall, you do it with all your might. You hit in between the studs. You know, you're probably okay. The wall's probably not. It'll have a hole that you got to patch, right? But if you hit the stud can withstand a bigger force than your hand. So your hand will break before the stud. Now, the stud still got the same action force as your hand did, right? Because for every action force, there's an equal and opposite reaction force. Now I'm going to give you one more example, and I'm going to have you type this in. All right, here we go. Ready? So you're driving down the road, and you hit a bug. You know, you're going like 55 miles an hour. You hit a bug, splatters on the windshield. Which experiences the bigger force? The bug or the windshield? So type in your answer. See, and this is why you guys are in physics. They are the same. That's right. You guys are making me feel good. Okay? So the force that the bug experiences, exactly the same force as the windshield experiences. It's just that the windshield can withstand a bigger force, so it doesn't break. And if you've ever, some people like to have their hand out the window when they're driving, right? If you've ever hit a bug, I may have done that before. It actually stings. It doesn't feel good, right? Or if you're on a motorcycle without, without a helmet with a face shield and without, a shield in front of you, the fairing, it doesn't feel good when you hit a bug. Just saying. So anyway, forces are equal and opposite. All right. Now I have another question then. So let's think about two different scenarios. Okay. First of all, I know that for every action force, there's an equal and opposite reaction force. So if that's true, then why isn't the net force acting on objects always zero? So let's go with this example first. So I have the action force. I have a bat hitting a ball. Now the reaction force would be the ball hitting the bat. Those forces have to be exactly the same amount in opposite directions. So why is it that the net force isn't zero? Why is it that the ball actually travels off of the bat and goes forward? Can someone explain that to me?
Because of the force applied.
Okay, so you're getting close to the right answer. It does have something to do with that. Let me show one more thing that might make it more obvious. Okay, so the action force was the bat hitting the ball, right? And I said it, but I don't know if everybody caught it. The reaction force is the ball hitting the bat. Are those two forces acting on the same object? Isn't the first force acting on the ball and the second force is acting on the bat? Do you guys see that? So these two forces are not acting on the same object. Because they're not acting on the same object, they can't cancel out. One force is on the ball, one force is on the bat. They're not on the same thing, right? And in fact, if you've ever swung a bat at a hard ball and hit it off the sweet spot of the bat, you know that reaction force, it can hurt, right? Because if you don't hit the ball in the sweet spot, the bat like starts vibrating in your hand and it doesn't feel good. Now maybe you guys have never had that experience because you're way better baseball players than me, right? I'm actually not that good at all. But anyway, so yeah, it's not because of the force distribution, although that's a good thought too. It's solely because these two forces are not acting on the same object. One force is acting on the ball and it's causing it to accelerate forward. The other force is acting on the bat and it's causing it to accelerate backwards. Now, how about a rocket? So Newton's third law, you guys, this is rocket science. We're learning rocket science today. So I have an action force. And that action force would be a rocket pushing on the exhaust gases. So the rocket pushes the exhaust gases down. What would be the reaction force?
It getting off the ground.
Okay, well, kind of, right? The rocket will move off the ground, but like, I want to show you guys that. So the action force here was the bat hitting the ball. The reaction force, ball hitting the bat. So the action force here, rocket pushing on the exhaust gases. The reaction force,
The exact exhaust gases pushing the rocket.
that's exactly right. So it's the exhaust gases pushing on the rocket. So the exhaust gases go down, the rocket goes up. One of the things that we do in class to teach you guys this is we actually have a balloon car race, and so that's what you guys are going to do next week. But our balloon car race is just a 1 day fun thing where I give you a balloon and some materials, and you have to build a little balloon rocket actually, that goes from the back of our room to the front of the room when I attach it to a piece of fishing wire. Okay, um, it's just a fun day, a fun way to learn these laws. But that balloon car works exactly the same as the space shuttle or any other rocket. The rocket is going to push the gas out, so the gas goes down, and then the gas pushes on the rocket in the opposite direction, so the rocket goes up. So these forces are acting on different objects. One object will accelerate in one direction, the other object accelerates in the other direction. So to see if you really understand this, I have the following setup. All right. Let's say that I take a boat, a sailboat, so it's got a sail, and then I get a huge industrial fan, and I blow the fan at the sail. Now, this is one of the things that people will try to do with their balloon rockets, and I'm going to give you a hint. If you do that, it won't go anywhere. Does anybody have any ideas why?
Because the air is blowing onto the white thing and it's not gonna go anywhere because there's like a barrier blocking it.
Okay, well, you're on the right track. Okay, so I want you guys to think about this for a second. I have the fan, right? Fan's pushing air on this sail. So the fan's going to push air on the sail in this direction. That would be the action force, the air pushing on the sail. Now, usually, right, what happens is that this sail is going to pull this boat forward. But the problem is this. Right here in this fan, right? Because this is all internal, all of these forces, they are acting on the same object, right? Because this sail is attached to the boat, and then this fan is attached to the boat, so the fan's pushing out air, the air's pushing back on the fan. All of these forces here, they're all going to end up canceling out. Because I have air going this way, I have air going this way, like nothing will work. In order for this to work, you guys, I have to get rid of the sail and I have to turn the fan around. So you may have seen these boats before. Has anybody ever seen one? No? Not on a TV show or anything?
Yes.
Yeah? Okay. Where you usually see these boats is in swamps. So you'll see them in the Everglades. You'll see them around New Orleans. And the reason you see them in swamps is because swamps are really shallow. Okay? So like even now, I like going on the Des Plaines River, and I don't always want to paddle, so I bring my trolling motor on my canoe, right? The motor has to go into the water. And if it's super shallow and there's all kinds of rocks here, the motor will get caught. It's no good, right? So what you do is you take a boat. These are called John boats. They are very shallow boats, so they don't sit very deep in the water. And instead of a motor, you put a fan. Now, this is like a rocket, right? The action force is the fan pushing the exhaust gases out the back, and the reaction force is the exhaust gases pushing the boat forward. So this is a good example of action-reaction. Here, there's all kinds of action-reaction pairs that are canceling each other out. And it's because of that sail. Here, you just made a little rocket and you're cruising around. And by the way, the reason that he sits up so high here is so that he can see shallow areas to try to avoid hitting him and beaching his boat. So...